Atwood machine is a device consisting of two masses connected by a cable over a pulley, and it's used to aid in the lifting of one object by using the second as a counterweight. And it works as long as the pulley can support the weight of both. So suppose here we're given the masses of the two objects. We would like to determine the acceleration that will result and also the tension in this cable here. We can tell that since the masses are connected by that cable, they will have accelerations with the same magnitude since they're moving as one. And we'll proceed with our free body diagrams and then think about the axes here. So, free body diagrams. For mass 1 here, tension and gravity. Mass 2, also tension and gravity. And if we're going to use the massless string approximation here, then we know that the tension at one end of the string equals the tension at the other. Thus, these two tensions can represent a sort of Newton's third law pair. And I'm going to put these two masses into a system, so they'll represent an internal Newton's third law force pair for that system. Here, clearly, we've assumed that mass B is greater than mass A, hence the rankings there. So to get the whole system to accelerate, we can see that the force of gravity on B has to be greater than the tension, which has to be greater than the force of gravity on A. Okay, so the axes then. We've got a pulley system. What we want to do is align the axis with the acceleration. Now, B is accelerating down, but A is accelerating up. We want them both to be accelerating in the same direction. And so we define upwards to be our positive y direction over here. And we want downwards to be the positive y direction over there. So they're both accelerating in the positive y direction. And we make that happen by allowing our axis to bend around the pulley, following the string, making a full 180-degree turn. And there is our bent axis for the pulley system. Okay, now we're going to get that acceleration by using step 1 of our procedure here. And we'll need a system. We're going to put A and B inside that system. So the system will include mass A and the string. It doesn't include the pulley. It does include mass B. And we're ready to write down Newton's second law for that system right there. Okay, here we go. We need just the external forces on that system, just the external forces in the y direction. So here, on this side, our y direction is upwards. Ft, that's an internal force that's acting between objects A and B, so that's internal. The only external force is FGA, which is in our negative y direction. It is downward, which is the negative y direction over here. So it's minus an FGA, and looking at the free body diagram for B in our system, that's an internal force. That's external because it's due to an interaction with the Earth, which is outside the system, and it is pointing down, which on that side is the positive y direction. So even though both of these weights are pointing downwards, this one is in our negative y direction, and that one's in our positive y direction because of the way we've bent the axis. Hence, we have FGB minus FGA. This force here is trying to pull the masses like this, and this force here is opposing it. Okay, so there's our difference in the forces of gravity for the total mass of our system, and if we can replace those with MBG and MBA and MAG, then we've got the acceleration of the system just in terms of our givens. So that's step 1. Maybe if I factor out a G here, I could rewrite this once more looking like that. And in this form, it's easy to tell that the acceleration we're going to get depends on the difference between the two masses. So I guess we've proven here that the system is guaranteed to accelerate as long as the two masses are different. We can also see that if you put the same mass on either side, the acceleration will be 0. That system would then be in dynamic equilibrium or static equilibrium. And furthermore, even if mass A was bigger, then this value here would be negative, just indicating that we would still be accelerating, but in the opposite direction. In that case, we'd be accelerating like this in our negative y direction, and this would still give us the correct answer. So this result is valid for all 3 cases. mass is equal, mass B greater, or mass A greater. Okay, but that's just step one. We now want to find the tension, our internal force. So we're going to go to N2L for just one of the two objects. Let's pick mass A here. I'll do Newton's second law. Here in the y direction, we've got tension upwards, positive y direction, gravity downwards. So it'll be tension minus gravity in the sum of forces for mass A. There we go, tension minus the weight of A. And then let's just algebraically rearrange this to get tension by itself. A few lines of algebra. And there we have it, tension isolated. We can substitute in our earlier result for the acceleration right there, since we know that both masses and the center mass have the same acceleration. And that concludes solving for what we wanted to solve for. I suppose that if you wanted to do the algebraic follow-up here, actually substitute these variables into there and continue and proceed without numbers, you could simplify this expression down to this expression. I recommend you try that out.